Hello there, and welcome to this edition of Calculus. So today's lesson, I do like to be upfront and honest with students. This lesson is not very exciting, but it is necessary in terms of derivative and integral rules that you'll just kind of have to know and memorize. And I'm not a big fan of that kind of math, but that sometimes it just is what it is. So. We've talked about how to differentiate e to the x. The derivative of e to the x is e to the x, and the integral of e to the x is e to the x plus c. Well, now this lesson, about a couple different things, but we're going to differentiate and integrate exponential functions other than base e. So, we might differentiate 7 to the x instead of e to the x, or integrate 2 to the x instead of e to the x. And the first thing I'm going to show you is where this derivative rule comes from. And so here's where it comes from. There's this process that a lot of times in math, it's not used too much in AP Calculus, but as you go on in higher levels of math, there's this differentiation process called logarithmic differentiation. Logs and exponents work really nice together. And so let me just show this process to you. So if I want to find the derivative of 7 to the x, then here's what we're going to do. We are going to take the natural log of both sides of this equation. So I would have the natural log of y equals natural log of 7 to the x. And now that I have this exponent inside the natural log, I can move the x out in front. So all I'm doing is rewriting this equation. I haven't done anything with derivatives yet, but all I've done is rewrite the equation in a different form, because that takes care of the exponent. And now I can go ahead and differentiate both sides of this equation. I'm going to differentiate with respect to x. So when I differentiate the natural log of y with respect to x, well, the natural log of y is 1 over y. But remember implicit differentiation. It's been a while since we've done that, but anytime you differentiate a y term with respect to x, you differentiate it, and then you put dy dx. So that's the left side. The right side, well, now we're just differentiating x times the natural log of 7. And this sometimes throws students off, but remember if I said to differentiate 3x, the derivative is 3, it's just the constant? Well, natural log of 7 is just a number, it's just a constant. So when I differentiate natural log of 7 times x, it's just natural log of 7. Well, we're trying to find dy dx, so now I can multiply both sides by y. I'm running out of room. Should have given myself more space. We're almost there. I want my equation to be in terms of x. So I need to replace y. Well, if you look back at the beginning, y equals 7 to the x. That means my derivative is 7 to the x, because that's what y is, times natural log of 7. So that would be the derivative of 7 to the x. The derivative of 7 to the x is 7 to the x times natural log of 7. So you could go through that process anytime you're dealing with exponents. This is a process that is available to you, but this is also a rule we can just memorize. If we are taking the derivative of an exponential function, then it is the exponential function itself. Just like the derivative of e to the x is e to the x, the derivative of a to the x is a to the x, but then we have to multiply by natural log of the base, which is what happened here. We multiplied by the natural log of 7. And you're really doing that even when you do e to the x. If you would find the derivative of e to the x, well, it's e to the x times natural log of e, which is just 1. And so that's why we get back to here. So you are using this rule even with e. It just so happens that natural log of e is 1. We can also differentiate if a, or that constant, is being raised to some function of x. We just have to do chain rule. So the derivative of a to the u is a to the u times natural log of a, same rule. But then we would have to multiply by the derivative of that exponent, chain rule, so times u prime. So that's how we differentiate bases other than e. It's just the same as the original function times natural log of the base. Well, we can also integrate exponential functions other than base e. It's pretty much the same rule. So the integral of a to the x is going to be, this is your rule, a to the x, but instead of multiplying by natural log of the base, we are going to divide by the natural log of the base. And then plus c. So that's our integral rule with functions other than e. So if I want to integrate 2 to the x with respect to x, well, it's going to be 2 to the x divided by natural log of 2 plus c. These problems, and I'm going to be honest with this entire section here, if you see one of these problems show up on the AP test, there might be one, there might be none. I would be shocked if you would see 2 problems from this entire note outline on the AP test. I have seen them show up. They are very rare. They don't like to test memorization per se. They like to test conceptual understanding, but they can show up. So I do think it's my responsibility to make sure I show them, even if they don't show up very often. Well, we can integrate 2 to the sine of x cosine of x. And that looks really, really messy. It looks a lot tougher than 2 to the x until we remember we have u substitution in our back pocket. Remember I said try to find u to be something where the derivative of it shows up elsewhere. So like if I have sine of x be my u, the derivative of sine of x shows up right here. So u being sine of x is going to be a really good candidate. So u equals sine of x du equals cosine of x dx, which is what we're trying to replace right here. So that's our du now. So now we have the integral of 2 to the u du. And we are essentially in the same exact place as we were in the previous problem. So now the integral of this is going to be 2 to the u divided by natural log of 2 plus c, and then replace the u. So 2 to the sine of x divided by natural log of 2 plus c. Good morning, AP Calculus students. So this next chapter that we are going to embark on is not a crazy long chapter, and the good news is it uses a lot of the same concepts as what we just learned in this last chapter. We're going to be integrating, we're going to have to remember to put plus c, we're going to do definite integrals, we're going to be integrating rates of things. Like, it's a lot of the same ideas. What happens in this chapter is we're going to learn about more functions that we can find derivatives of and we can find integrals of that we haven't yet learned. To be honest with you, it is a good amount of rule memorization. Some students like that, some students don't like that. It is what it is. But our lesson today, we're going to be dealing with inverse trig functions, meaning like sine inverse, tangent inverse. To remind you, if you see arc sine, that is the same as sine inverse. Okay, so when you see arc sine and sine inverse are synonyms of each other, and they'll put both on the AP exam, and I'll put both on ours, okay? So we have to know that. Now, we're going to talk first, the first half of this note is just how do we find derivatives of inverse trig functions? And like I said, it's just rule memorization. The good news is, I will say this, I'll be honest with you, these problems show up very, very little on the AP exam. Now, those of you going into Calc 2 and beyond, you might have to deal a lot more with inverse trig. It's a big thing, but in our course, it's not asked about a ton. A little bit, but not a ton. So here are our rules. I'm going to put the rules here and then kind of give you a couple examples of how they get used. So if I want to take the derivative of sine inverse of u, or arc sine of u, remember u is a function of x. Like u, for an example, u could be 2x right here. So 2x would be what u is. We kind of did that with natural logs. Here's our rule. If I want to take the derivative of sine inverse or arc sine, it's the derivative of the inside, so u prime, over the square root of 1 minus whatever the inside function is squared. That's our rule. Those of you that make flashcards, you do whatever you do, you just got to memorize it. Now, the nice thing is, it looks like there's 4 here we're going to have to memorize, but the inverse cosine is literally just the negative of the inverse sign. So you really just need to know sine inverse, and then you already know cosine inverse. It's the same, it's just the negative. So negative u prime over 1 minus u squared. Here are rules for arctan. Arctan is going to be the derivative of the inside. So the nice thing is they all start the same. It's the derivative of the inside over, and then this one's going to be 1 plus the inside squared. This one's a little nicer. It's a plus sign, which everyone likes. There's no radical. But it's the derivative of the inside over 1 plus the inside squared. And then arc cotangent, literally just the negative of that. So negative u prime over 1 plus u squared. So here are really just two rules that you're going to have to know. And here's how they get put in practice. So if I have arc sine of 2x and I want to find the derivative, well, I'm going to apply the arc sine rule right up here. So in this rule, u is 2x. So here's what this would look like. It's going to be the derivative of the inside, so 2, over the square root of 1 minus the inside, so the quantity, squared. I mean, it's not a crazy tough rule. It's just one you got to know. If you would clean this up, it might look like 1 minus 4x squared, because you would have to distribute the 2 to the 2 and the x. And then the last example for derivatives, and then we're going to talk integrals. So if I want to find the derivative of tan inverse, or arctan, we're going to be using u prime over 1 plus u squared. So let's do it. So it's going to be the derivative of the inside. So the inside is x, so just 1 over 1 plus the inside squared, so x squared. Now the reason I end with this one, okay, so we have these few derivative rules that we're going to have to know, but the reason I end with this one is when we get into the integration. So the integration gets a little tougher. You know, I've said integration gets tough. Integration does get tough because at this point, all you know is the power rule and you know u substitution. But there is more. Based on how a problem looks, determines how you attack that integral. And so we do have a few more integration rules to learn, and they all look pretty similar, which makes them pretty tough. So here's the reason why I ended with this one right here, okay? So now, look at what happens if we go backwards, which is what our first integration problem is right here. If I integrate 1 over 1 plus x squared, it's kind of a formula. These two things right here, this one and this one, are essentially our formulas that we're going to have to be on the lookout for with integration. You know, with integration right now, if I see this, I would try to do u substitution. That would be me. I would try to have u be this denominator and then go through u substitution. But here's what I've said. You want to have u be something where its derivative shows up elsewhere. And look what happens. If I have u be 1 plus x squared, its derivative is 2x, and there's no x anywhere else. I get stuck. Bottom line, u substitution is not going to work. We just have to recognize if you have 1 over 1 plus x squared. We have to recognize this form. This becomes arctan of x plus c. 1 over 1 plus x squared is arctan of x plus c. And if we have 1 over the square root of 1 minus x squared, well, look, that's our arc sine formula, essentially, right here. So this one shows up a lot less than this one. This is the one you're really going to have to know, I would say. Out of all this that you're learning today, that's the big one. But this one would become arc sine of x plus c. And that's it. Now, here's the deal. Here's what's going to be happening, okay? Look at this first example. This first example is 1 over x squared. Now that you know this arctan rule, you're going to be tempted to be like, oh, it's 1 over and then it's x squared. That's arctan. Well, no, it has to have the 1 over 1 plus and then something squared. That's how you know it's going to be arctan. It has to look just like this. Now, there's a little wrinkle to that I'll talk about here, but if you notice, this doesn't look like that. It's missing the 1 plus on bottom. But you'll be tempted, but you already know how to integrate this. You've already done this several times. You can just rewrite this as x to the negative second, and then you use your power rule. I can increase that by 1 to get x to the negative first, and then divide by negative 1. So it'd be negative x to the negative 1 plus c. So there's no arctan involved. And eventually we're going to have to deal with what if it's 1 over x? We're going to have to deal with what if it's x over 1 plus x squared. This happens in our next lesson. Look, these look really similar. But this one's not arctan. It has to be 1 over, so basically a constant over a quadratic. 1 plus a quadratic. This one in our next lesson, we're going to learn, we'll have u be the denominator, and u sub is going to work because the derivative is 2x, and there's an x here we could deal with. So we have, look, we have one fraction here, one fraction here, one fraction here. They all look similar, but they're all going to be handled differently, and that's when integration gets hard. When the problems look the same, but we have to attack them differently. You don't get to pick your favorite method and apply it. And we'll get practice with this. You're not going to feel comfortable right now with all this, but we'll get practice with this, I promise. So look here. This one looks similar to this one. You have a constant on top. It's a 3 instead of a 1. You have something being squared. You have 1 plus something being squared down here. This is the only other weird thing that can happen, and here's how we're going to attack this, okay? This 3, I'm going to pull out in front of the integral, because we could pull constants out in front. Here. And now, you pretty much do have this form. You have 1 over 1 plus, and then something squared. Notice in the formula, this is really important, the thing that was being squared here, the x, just went inside the arctan. That's what's going to happen here. The thing, the x plus 2 that's being squared, is going to go inside our arctangent. So for this one, instead of just being arctan of x, it's going to be arctan of x plus 2. So this would be 3, and then this is going to be arctan of x plus 2 plus c. So we're still using that formula. This is almost the hardest that I can make these problems is right here. Like I said, in Calc 2, these can get a lot nastier, but not for us. We really just have to recognize the form. The last thing that can happen, okay, again, we're going to talk about different integration methods. You're not going to like this one. That's okay. It's my duty to show it. I can't say that it's going to show up maybe once, if at all, on your exams. Okay? So you have a constant over a quadratic, but it doesn't look like this. So if you have a constant over a quadratic, you're going to have to do arctan. Our objective is to make this look like this, or this right here. And the way we do it, you're not going to like this, but the way we do it, we have to use what's called completing the square, which you learned back in Algebra 2. I'm guessing you did it in pre-cal. We have to do completing the square. And here's what this looks like. So we're going to do completing the square on bottom. Essentially, I'm trying to get to a quantity squared. 1 plus a quantity squared. So here's what this is going to look like. So if you remember completing the square, we want to create our own c-value. We don't like their c-value. We want to create our own c-value right there. Okay? We're going to put their c-value just right here on the end. Now, I want to create our own c-value, and here's how we do it. We take half of the b value, so 3, and we square it. You take half of b squared. So 3 squared is 9. Now, if you remember back in Algebra 2, you can't just randomly add 9 here. You have to counteract it. So if we added 9 here, we have to subtract 9 here. I screwed up on this problem. I need to change this when I typed it. So I want this to be plus 10 at the beginning because it's supposed to turn out a certain way. So I botched this one. My bad. I'm the worst. So let's pretend that C value is plus 10 to begin with because it does have to work out a certain way. So we took half of B and squared it. We got a plus 9. So we have to subtract 9 here. So basically, look, we did nothing. We've done nothing. We added 9 and subtracted 9. So you might be like, well, then why did we do it? Well, here's why. So after you create your own C value, now you're going to factor this quadratic. And what happens every time, it turns into a quantity squared. If I factor this, this would be x plus 3, which we can write as x plus 3 squared. And then the 10 minus 9, that just becomes a plus 1 on the back end. The reason I said it has to turn out a certain way, it's always going to have to be 1 plus something squared. It has to, or you can't use these formulas. And so that plus 1 had to happen here. So if you really want to make it look like the formula we're using, you can write this as 1 over 1 plus x plus 3 squared. And now you have this that we just did in this example. It's literally the same thing. This is a very, very unlikely thing to occur, but it can occur. And so if you integrate this, this is our arctan format. Arctan of x plus 3, so the thing squared, plus c. I know that's a lot to chew on, and you're going to be, your head might be spinning, and that's okay. But I just needed this out there so that when we get into our next lesson with, e to the x and natural log of x, we have some understanding of this, and you'll see why integration gets tough. But we'll get practice with this, just not quite yet.